All right. So we want to thank you guys that are in the audience and those who are looking at us by live stream. Welcome to our first lecture in the Dwayne L. Ford lecture series. And it's pretty interesting. I don't know if it's corny or coincidental. You tell me. Today, our speaker comes from Golden, Colorado. Andrews University AU stands for gold. This is our 50th year, which symbol is gold. Okay. What he has up on the screen, and one of the motivating factors, is the Gold King Mine spill in Colorado. And it's pretty interesting that this is what we get started with for our 50th anniversary of the seminar program and the 75th year of our department. So I'm sure that most of you have read all of the emails that we've sent you about the speaker. And what I'm going to say in terms of introduction is that he is well respected in this field, and he's highly sought after. And so he's gotten, since this spill, he's gotten lots of interviews from the media, and he's been called before the Congress to discuss this issue. So I hope every one of us pay attention. And I think this talk today is not going to be specifically on the gold mine spill. It gives a context for what he's going to speak about. We will be covering chemistry. Okay. So again, I want to thank you very much for accepting our invitation to be here with us today.
My pleasure. Thank you for the introduction, and thank you for the opportunity to give this presentation for the 75th anniversary of the chemistry department and the 50th anniversary of the seminar series. It's a real honor and privilege. I'd like to start out by saying that the title about gold mining and its impact on the environment is too broad and it's too narrow. It's too broad because when we talk about gold mining, we talk more than just about acid mine drainage, which will be the main theme of the topic here. We talk about things such as cyanide leaching and how to deal with cyanide, the chemistry of cyanide, the treatment of cyanide. Then the gold ore goes through processing and it produces a waste product of and chemicals known as tailings, and we have to look at the chemistry of the makeup of the tailings and the engineering of how we contain the tailings and minimize the damage to the environment from those tailings for the long term. So it's too broad a topic to say gold mining because of all those factors, and obviously we can't cover all those factors in 40 or 50 minutes. And it's too narrow because acid mine drainage is not just associated with gold mining, but with all what we call hard rock mining, metal mining, and also the potential is there with coal mining. And in fact, tens of thousands of miles of streams on the East Coast are contaminated with acid mine drainage from coal mining. So our focus will be on acid mine drainage, and with an emphasis on gold mining. And the gold mining because, as Dr. Murray has said, that infamous spill, the Gold King mine spill in Silverton, Colorado. Now, I'm looking at the audience here, and I may not be able to resolve it completely, but how many people have read about or heard about the Gold King spill? Okay, so people have heard about it. What we're seeing here is a picture on the right of the mine portal or mine opening. This is where the spill broke through. The mine portal had collapsed, and there's another collapse behind it, and water built up behind those blockages. And it burst through, and it ended up emptying into Cement Creek, which then went into the Animas River. And over on the left-hand side, we'll see the Animas River. The train is a steam locomotive, and it takes tourists from Durango, Colorado to Silverton, Colorado, a magnificent trip. And these may have been the first people to have seen this spill. And obviously the water looks terrible. And I'm going to say something that could be controversial. It is not as bad as it looks. And I'll tell you why shortly. It looks absolutely bad with that yellow-orange color. That yellow-orange color is really iron. It's the iron that's associated with the particles that came out from the spill, as well as in the water, and it gets oxidized when it gets exposed to the atmosphere. And you get that yellow-orange, which is known to the old-time miners as yellow boy. And this is something we see with acid mine drainage. Now, as I mentioned to you, I said it's not the epic disaster some people made it out to be. Oh, it's nasty, and this is not something that you want to see. But let's get some perspective here. You may have heard that it was 3 million gallons that spilled. Sounds like a lot. But let's look a little more into this. 3 million gallons. Okay. In Colorado, that volume of acid mine drainage enters headwaters of 40% of the Colorado rivers every 2 days. In other words, the amount of the spill enters river waters in Colorado from inactive and abandoned mines every 2 days. Another perspective, 3 million gallons is 400,000 cubic feet. Cement Creek flows at 750 cubic feet per second. That's 8,400,000 cubic feet per day. So it's 400,000 cubic feet of waste into 8,400,000 cubic feet of water per day. So there's a 1 in 20 dilution factor. That Cement Creek enters the Animas River that flows even more greatly, and there's another dilution factor. What that means is by the time that water moves through by major towns like Durango, it has been diluted many tens of times. It still looks terrible, and it makes sense to close your drinking water plant intake in order not to take this water in. But the fact is that it's not as bad as many people made it out to be, and it's a fleeting moment. This is a plume of waste that moves through and passes by. And what happens as this waste moves along the river? Well, as it moves along, it spreads. It spreads out, and the peak concentrations of the nasty materials, things like metals and acidity, they will decrease in concentration. And I made up a little slide for us here. And what we see is we have this nasty spill, and I think you can tell it's nasty because look how deep red it is. Now imagine a normal curve as our spill. Okay, you see the peak concentrations here. It moves downstream. So here's the spill in Cement Creek. It moves into the Animas River and down to Durango. What happens is the spill spreads. And as it spreads, the peak concentrations come down. And then it goes into Mexico where the peak concentrations come down and it spreads more. By the time you get to Lake Powell in Utah, I'm willing to state that you will not be able to detect that there ever was a spill in the first place. Now, on top of that, if we look at this normal curve, if this is passing by Durango and this is the tail end of the spill, what happens is as the spill passes by, it gets back to pre-spill levels. Okay, now, as it turns out, I predicted that would happen in a few days. And when EPA went out and did the measurements a couple of weeks later, indeed, it is back to pre-spill levels. Now, I did not say background levels. Background levels are natural levels. But the Animas River has been taking acid mine drainage for over 100 years. It's not at natural levels. It's at pre-spill levels, which were too high, actually. In fact, they have trouble establishing fish in that river. Now, people will say, great, I understand that. However, what about the solid particles that settle to the bottom along the bed of the Animas River? Won't that allow metals to enter the food chain and contaminate our fish? Well, that's a good thought. If there was enough sediment of high enough concentration of metals on the sediments, then I'd say, yes, that's a problem. But much of the dense, heavy sediments dropped out in Cement Creek. And not much, I predicted, would come out on the bed of the Animas River. And that which came out on the bed of the river will get resuspended with every rainstorm. And when the snow melts in the spring, the flow will pick up so much, it will scour that residual, dilute it, take it downstream, and disperse it, and the problem is over. And in fact, some of the measurements that EPA has taken of those sediments show that there aren't much in the way of those sediments, and the level of metals on those sediments are higher perhaps than what we would like to see, but they're not terribly high, and they're actually lower than some locations where they sampled upstream of the spill. And that's where the area has been taking acid mine drainage input for a long, long time. So what I'm saying here is that the problem wasn't as big as it was made out to be, and it's only temporary. Not everybody will agree with that who have special interest in the area, but so far everything I've said seems to have come to pass, thank goodness. Otherwise I'd look like a fool. Now, I've written 2 articles for an internet publication called The Conversation. It's basically a nonprofit publication to give real academic rigor to articles in social sciences, technical fields, and give a little journalistic zing to it, but to give you more than what you get with the typical press. And I have listed there the sites for the 2 articles. One was an article right after the spill where I made predictions based on strict science, and the other one is what happened after there were measurements that were taken to see if, in fact, my predictions had come to pass. So it's not as bad as it looks. And I think science and chemistry dictate it when you evaluate it that it wouldn't be as bad as it looks. Another factor is that people are saying, how can this happen? EPA triggered this spill. This is not unusual. The same area had a big spill in 1975, and also from inactive abandoned mines. And in 1978, there was another spill in the same place. And people interviewed said, oh yeah, we've seen this before, if you've lived in the Durango area, because of these previous spills. You have thousands, tens of thousands of abandoned inactive mines, and all of them represent potential environmental impacts, and some of them are leaking acid mine drainage intermittently or consistently into the water. And remember, as I said, in Colorado, the volume of this spill enters Colorado rivers every 2 days from inactive and abandoned mines. So this is not an unusual phenomenon. Now, to show you how not unusual it is, this particular Clear Creek is where they discovered gold around 1859 in Colorado. And this is a spill that occurred in Clear Creek from an inactive mine in 2009. And it looks just like what we see in the Animas River. And it passed by and it went through, and eventually the river recovered within a couple of days. Again, this is not an unusual phenomena. And until these inactive abandoned mine sites are taken care of, then we're going to have more of these, and probably more often as these mine sites age. Well, the water can indeed be toxic. As we can see the evidence here, of the young person laying there in the stream who was exposed to too high levels of the metals in this particular water. I don't know if you can resolve that picture at all. Can you see anything unusual in that picture? Like the label on the student's back? Okay, well, it says Andrews. At any rate, moving right along here. I take some liberties with my slides. Okay, so let's talk about this acid mine drainage. What is it? Well, it's the drainage that comes from activities such as mining, where you take pyrite, iron sulfide, also known as fool's gold, and you expose it to an oxidizer, air, really oxygen, and you expose it to water. Once it's exposed to air and water, it undergoes oxidation reactions. And what you get out of it has been known acid mine drainage. It's also been called acid rock drainage or mining impacted waters. It has primarily two characteristics. It's highly acidic in nature, and it contains high free metal concentrations, and those metals are dictated by the minerals that are in the area. You may have iron, zinc, copper, lead, cadmium, arsenic, etc. And it turns out that the more acidic the water, the more easily the metals are dissolved in that water. Okay, so if you happen to see the picture on the upper right, that picture's a self-portrait representing what it's like to work at Colorado School of Mines. Okay, so now if you do get this acid mine drainage, what is this water suited for? Nothing. You can't use it for drinking. You can't use it for irrigation. You can't use it for watering your livestock. You cannot even use it for industrial purposes. If you draw that water with acid mine drainage into your boiler, it's going to form a scale and it's going to ruin your boiler. Essentially, it's useful for nothing. And what we'll see here is that these sort of things happen around the world in mines. This, I don't know if you can see my pointer, but in the lower left-hand corner, the upper right-hand corner picture, that's the Fisher Mine. It empties into Fisher Creek. It's right on the border of Yellowstone National Park, and it enters the most pristine river in the United States, the Yellowstone River, with acid mine drainage. The impact can be great. I work in South Africa every year for about a month, sometimes more, and this is a picture from one of the spills that occurred there, and you can see the acid mine drainage. This was not from a mine opening. This is from a tailings storage facility, the processed waste, and it burst and it flooded. And not only did it flood this wetland out here, but it also flooded out 2 informal villages. And so the effects were very drastic. It's a problem, acid mine drainage. Now, if you want to understand acid mine drainage and how to treat acid mine drainage, you need a knowledge of chemistry. It helps to have some geochemistry and some microbiology as well. But chemistry is the key. That's why these people here are studying so hard. Okay, so acid rock or acid mine drainage. A fellow named Jim Gusick came up with this acid rock drainage tetrahedron, which defines what you need to make it happen. You need water. You need an oxidizer, and air, really oxygen. But even ferric iron, Fe3+, can act as an electron acceptor or an oxidizer. And you need pyrite. But what else do you need? You need microorganisms. The fact is that the reaction will occur with just water, an oxidizer, and pyrite, but it's very slow. It's been shown that the microbes can speed up the reaction by 1,000,000 times. Now, with that speed up, you might say, well, where do you get the microbes that make that happen? I'll tell you what, if you have water, you have oxygen, and you have pyrite, you will find the organisms, like thiobacillus, ferrooxidans, and other organisms. If you find those particular organisms, it means you have water, air, and pyrite. They're so intimately involved in this particular case. That's the tetrahedron. And this was from a study that was done. And if you take a look here, from 0 to 1, this is a 0 rate of reaction to the maximum 1 rate of reaction. And this is pH level. And what you see, if you just have the chemicals, how low the reaction rate is. But when you have the microbes, look at the reaction rate. Okay? And it peaks up around pH 2 to 3. Now, remember I said if you have an oxidizer that is iron 3, ferric iron, that will attack other metal sulfides. It'll attack pyrite. Yes, it'll also attack marcasite and chalcopyrite and chalcocite and sphalerite and all the other rites around. And the fact is, it will oxidize those and release those metals into the acidic solution. So depending on the minerals that are around, you'll get the copper and the cadmium and the lead, etc. Okay, so how is it formed? Let's look at the chemistry. Isn't that apropos for this particular program? Okay, you have enough water, you have enough oxygen around, and here are the reactions. This is the sum reaction. You take pyrite plus oxygen plus water, and it gives you iron hydroxide. Now, really, it's called iron oxyhydroxides, which are a suite of compounds that have iron, oxygen, and hydroxide in them. This is the precipitate you're seeing in that orange-yellow color, the yellow boy. And look at this. You get 8 moles of sulfuric acid. You get 16 moles of hydrogen ions. This is one of the most acidic reactions known. Acidic natural reactions that is known. Okay, there's actually several steps that occurs. And just going through them briefly, giving the limited time, this is the first reaction where you take your pyrite, FeS2, iron sulfide, with oxygen and water, and you get ferrous iron, which dissolves in the water. And you get sulfate, which is the sulfide that's been oxidized, and you get hydrogen ions. Okay, what happens is you get 2 moles, and of course, if you don't know what moles are, it's here. You have 2 moles of acidity generated per 1 mole of pyrite oxidized. The next step is the oxidation of the iron 2 to iron 3. So oxygen strips an electron off the iron 2. You get ferric iron and water. The next step, the ferric iron reacts with water. It's hydrolyzed to form ferric iron hydroxide, the yellow boy, the iron oxyhydroxide. And of course, this arrow says it precipitates. And 12 hydrogen ions, all that acidity. Now, keep in mind this ferric iron, because we're going to come down here to this step. The ferric iron acts like oxygen. It's an oxidizer. It will accept electrons in a redox reaction. And it will oxidize your pyrite into iron 2 and sulfate and 16 hydrogen ions. This is the series of reaction generating the tremendous amount of acidity. This ferric iron can also attack other sulfide minerals to release those metals. So what kind of water might you get after you get the generation of this acid mine drainage? Now, this water is not particularly bad, but it's bad enough. But just to show you, the pH at the Argo Tunnel in Idaho Springs, Colorado, is 2.7. Stream standards range between about pH 6 to pH 8. Iron is 45 milligrams per liter. You want it to have 1 milligram per liter or less. Lead is in the water is 2.6 milligrams per liter. You want it to be 1,000 times less, 1/1000th, to meet stream standards. As you can see, this water is very, very much above acceptable stream standards. And I've seen iron at literally thousands of milligrams per liter. I've seen lead and cadmium at 10 milligrams per liter. I've seen the pH as low as 1. So this water is not nearly as bad as that. But this is nasty water. Now, if we want to treat acid mine drainage, we need to know what? Yes, we need to know chemistry. Okay? So chemistry, we need to know if we want to treat the acid mine drainage. Now, there are two broad classes of methodologies that are used to treat acid mine drainage. Active treatment, which is your conventional chemical precipitation, and that requires the mechanical addition of alkaline chemicals like lime to raise the pH, precipitate out metal hydroxides, remove those metal hydroxide sludges. It's expensive. And there's a so-called passive treatment. Now, that used to be the name, meaning that you didn't have to add chemicals at all, and you didn't have to put in any kind of power. That's not true anymore. A better description is low energy input reactors that require minimal amount of operation and maintenance costs. And in those cases, you use naturally occurring chemical and biological reactions in a controlled system in order to treat your acid mine drainage. Active systems have certain advantages. One is that we know it works. It's proven. And it's founded on some fundamental equilibrium chemistry. And the regulatory community is very happy with it because they know it works. Disadvantages are that you have to add lots of chemicals. I have seen small sites buying 20,000 pounds of lime a week to add. And there are high operation and maintenance costs associated. Passive treatment systems, in theory, you shouldn't have to use chemicals. It turns out that it can be useful to add certain chemicals, but not nearly as much as you would do in the active conventional systems. And the energy needs in passive systems are not zero, but they're very small when you compare them to the active systems. And operation and maintenance costs are minimal. It used to be thought that you would never have to have operation and maintenance requirements. It turns out you cannot simply leave the system in perpetuity and hope it'll work. But it's much lower than in active systems. Disadvantage is that most of the studies done on these passive systems in the last 30 years or so have been at what they call the bench testing level. You know, maybe you have a series of 32-gallon Walmart trash cans that you're using. The full-scale implementations have not been particularly successful. They all have been promising. They're still promising. But if they don't fail immediately, they have a tendency to fail within 2 years. Or they don't treat effectively. And because of that, the regulatory agencies just don't have that warm and cozy feeling about them. But we'll look at some of them. The conventional active remediation techniques. It's all about equilibrium chemistry, folks. We'll call this method the ODAS, oxidation, dosing with alkali, and sedimentation. Generally, it's the addition of lime to neutralize the acidity and precipitate out the metals. As you can see at the bottom here, there's several other techniques. We're not going to cover them. We just don't have enough time for that. Now, active remediation defined. Paul Younger, out of University of Newcastle upon Tyne back in 1998, said that active treatment is the improvement of water quality by methods which require ongoing inputs of artificial energy and or biochemical reagents. It costs. Your goals, trying to get your pH between 6.5 to 8.5, to get your iron below 1 milligram per liter, and to reduce zinc, copper, lead, cadmium, all the various metals down to regulatory limits, and also try to bring down the level of sulfate in the water. And generally, what you do is you add alkalinity. Think about a neutralizing capacity, or I think in German it was Sauerbindswundsvermogen, or adding neutralizing capacity. And you're trying to bring that pH to near neutral. Why? Because your acidic water dissolves metals much better than waters near neutral. And if you can bring the pH to near neutral, you'll precipitate most of your metals out as a sludge, as a hydroxide sludge. Limestone and lime are the favorite products because they're inexpensive, readily available. Of course, limestone is calcium carbonate. More often, people will use calcium oxide, burnt lime, or quick lime. Now, calcium oxide is hard to handle. So you can make calcium oxide by heating up calcium carbonate, limestone, to form the calcium oxide. But it's hard to handle, but it's very effective. More often what they do is they hydrate the calcium oxide, they add water, and they get calcium hydroxide, and that's hydrated lime. And typically, that is what's used. Okay, now, each of your metals shows its own behavior and precipitation behavior at their various pHs, but you find that almost all of them will start to go to minimum solubility at near neutral pHs and above. And as you increase the pH of your acid rock drainage, ions such as iron, copper, zinc, lead, arsenic will react to form hydroxides. And here's the reaction, okay? Mn plus, okay? Copper 2 plus NOH minus. For the copper, it would be 2OH minus, yields MOHN, copper OH2. That's your typical reaction, and that's a hydroxide that is a solid that will precipitate. Here's a graph of metal concentration or solubility in water versus pH. Please note that this is a log scale. As you drop the pH, the solubility of metals increases exponentially, which shouldn't be surprising because pH is a log function. So you add the alkaline material, you neutralize the pH, you take it up to about pH 10, and you find most metals will be at their minimum solubility, and they precipitate out as these various hydroxides. That's the key reaction. Now, you have to design these systems. They could be very simple, and the one that's built just outside of the Gold King mine right now that's treating the water is just a pit that's been lined by high-density polyethylene plastic, and they're adding lime into the pit. It looks like, it looks like this. Here's your acid mine drainage. They add the lime. A sludge forms in the pit. You decant the water off the surface, and it has been cleansed of many of the metals. It works. You have limited control. You may not meet standards, but the water is a whole lot better than when it first came in. The sludge you do have to dig out and get rid of at a landfill. You can go a little more sophisticated, say to a pit treatment process. And the pit treatment process, you do have a pit, but you have a lime slurry that goes into a reactor with your acid mine drainage. That treated slurry goes into the pond to spend enough time so the material settles out. You have a barge with a pump on it, and that barge pump will pump the water from the surface out. If the water is highly alkaline in nature, maybe a pH 8 to 10, you'll neutralize it down to pH 7 and then discharge it. Oops, excuse me. Okay, or you can have a very sophisticated system like this, where you have the lime system, and you actually take sludge of the precipitated metal hydroxides back and mix it with the lime, add it to the AMD, and have a series of mixing tanks, and add a flocculant, and a flocculant will neutralize the charges on the particles so the particles can come together to large particles, and then in the clarifier, they can settle out faster. Here are the small particles up on top. You add the flocculant, they become bigger, and they settle out faster. And this is a completely engineered system. Okay, some pictures, dosing with alkali. You have acid mine drainage coming in. They dose it with alkali, and they send that over to a tank where the material can then start to settle, the hydroxides. Now, it seems to me that you have high sulfates, right? Remember that reaction oxidizes the sulfides, it forms sulfates. You also have calcium hydroxide, calcium sulfate. That's gypsum. These pipes are in South Africa, and what they did is they didn't design the plant properly, did not take into consideration that gypsum would precipitate in their pipes. These pipes started out with an 8 to 12-inch orifice, and once the gypsum started to precipitate out, it now has a 1-inch orifice. They had to remove these pipes. There's a field of these pipes that were no longer effective in the system. It's one of the engineering problems you have, which is a chemical problem of trying to make these systems work. Well, what happens then is you go to sedimentation, where you want the hydroxides to sediment out. The water comes in. There's a shield around here to break any kind of turbulence, because you don't want to suspend the stuff. You want it to settle out. And the material settles out, and it gets scraped up on the bottom by a series of what looks like windshield wipers that put it into a sludge collector, and you collect the sludge discharge. And here is a sludge collector with a person who's very knowledgeable in these things, who's making sure that it's operating properly. Oh, is there a problem? Okay. Anyway, moving on with the talk. What happens is, if you do this, can you get good treatment? And I'll just say this very quickly because we don't have a lot more time to go, is you can get many of the metals down to, say, 99.5% removal. Some metals you don't do as well. Lead, you may only get 80%. But generally speaking, you can remove much of the metals that are in the system using this conventional precipitation. This is a treatment system that's located on the Wonderfontein Spruit catchment. It means Wonder Fountain Stream in Afrikaans in South Africa. And what you're seeing here is the big lime tower that feeds the lime into the system. And the lime enters the system here, reacts. You get these mixers, and then it mixes more and more slowly. Then you have flocculators. Then eventually the material goes out to be into a settling pond. And this is what the water looks like that goes to the settling pond, where the hydroxides of the metals will ultimately settle out. Okay, in a big rush now, what if the passive treatment? The passive treatment has been looked at many years as a black box. In fact, you may have heard of what they call wetland treatment systems. And the wetland treatment systems, the idea was that people had noticed that mine water going through a wetlands was cleansed to some degree. Not real effectively, but it was cleansed to some degree. So let's go out and build constructed wetlands. Treat them as a black box. You have an input of mine water, an output of clean water, and everybody's happy. It's not a black box. Somebody needs to find out what are the mechanisms, the vehicles by which the pH rises and the metals are precipitated out. And we refer to it as sequential ecological extraction, or C. And this is sequential ecological extraction of metals in a human-made bio or geochemical system that resembles natural systems or processes. Now, definition of the passive system, it uses basically the common geochemical reactions typically assisted by microbes or perhaps plants. But nobody knew what was taking up the metals. There are many different passive systems: natural wetlands, constructed wetlands of various types, anaerobic and aerobic, limestone treatments, anoxic limestone drains. Again, we can't go through all these because of the limited time. Many different types. We will concentrate on the geochemical reactions assisted by microbes. Now, the idea of using a wetland as a treatment system has been a promising idea for over 30 years. As I mentioned, people saw that mine water going through wetlands can be cleansed to some degree. We don't know why, but it might work. And everybody hypothesized that it's the plants taking up metals, like right here, heavy metal uptake by plants. Okay, and people said, look, water went in dirty, it came out clean, it was the plants, but nobody was able to show it actually was the plants. As it turns out, it wasn't the plants. It also turns out that would you use a natural wetland to treat acid mine drainage? Given the loss of wetlands all around the world and around the United States, would you put degraded water from mine drainage through a natural wetland? This is a wetland where somebody said, let's use the natural wetland to cleanse the acid mine drainage. I don't think this is such a hot idea, do you? No, and you never know what you're going to find in the woods in West Virginia there. Okay, so what might be the removal mechanisms for the metals in these passive systems? Well, it could be microbial sulfate reduction and precipitation of metals as sulfides. In other words, there are microbes that will take the sulfate, reduce it to sulfide. The sulfide reacts with the metals to make metal sulfides. How did the metals start out in the mountain in the first place? As metal sulfides. And it precipitates out. Maybe the metals will adsorb or bind to the particle surfaces of the system. And you also can get in aerobic zones precipitation of ferric and manganese oxides. You can also get uptake of plants. Well, let's see what happens. What accounts for the removal of metals? And can we optimize the system for those mechanisms? Plants. Well, this is at the Big Five Tunnel in Idaho Springs, Colorado. And we built a system here to treat the acid mine drainage coming from this particular tunnel. And this is the water here that pools coming out of that tunnel. And we measured the tissues of the plants for 4 years. And basically what it showed, the plants were doing absolutely nothing. If you were to ignore statistical significance and say, well, maybe we saw a little bit of increase in the roots, stems, or leaves of some metal, and took the most extreme value we had, it would account for as little as 1% of the metal accumulation. Basically, the plants did nothing. So we can do away with the plant hypothesis. The adsorption hypothesis, whoops, let's go back here. The adsorption hypothesis, without reading the graph, was, okay, do the metals attach to the solid particles and get removed? So what we did is we took this material we use as the wetland substrate to plant the plants in, and we sterilized it so there were no microbes, and then we passed a solution with high metal values in it. And what happened was, for the first 20 days, all the metals were removed. Adsorption is occurring. But then after about day 20, the metals that adsorb most weakly started to break through untreated. And then all the other metals within 30 days broke through untreated. In other words, what happened was adsorption occurs, but eventually you saturate all those sites with the metals and it can absorb no more and it ceases to be effective. And if you want a system to last for a year or 4 years, adsorption is not going to do it. What about the microbes? Sulfate reducing bacteria. They take sulfate, SO4, they take organic matter, they reduce sulfate to sulfide, which is very reactive, and they produce bicarbonate. Oh my goodness. Bicarbonate will neutralize the pH. The sulfide will react with the metals to make metal sulfides, which precipitate. Great hypothesis. Does it work? Well, we built some of these sulfate reducing bioreactor cells, and we use all sorts of different types of substrates to see which is best. And we use radioactive tracers, sulfur-35, to look at the sulfate reduction activity of these bacteria. And what we found is that the microbes could account for all of the removal of the metals for a 2-year period simply by sulfate reduction and precipitation of metals by sulfides. It was the microbes. Okay, and here are some of the sulfate reducers. This is what they actually look like under electron microscopy, and this is an artist's rendition. Okay, so with the constructed wetlands, we can treat net acidic waters with low pH, high iron, and we can remove the metals from them and raise the pH. Here are several anaerobic reactors that have been built, that have been tested, have been fairly successful. And they're not wetlands anymore. They're engineering design, passive acid mine drainage treatment systems, and we call them sulfate reducing bacteria bioreactors. And what's going on in these systems is hydromicrobiogeochemistry. Okay, so if somebody says to me, what do you do for a living? I say, I'm a hydromicrobiogeochemist or a microbiohydrogeochemist. That's a very small geochemist. Okay, so here are some systems being constructed at the Bunker Hill Superfund site. They're putting these pipes in, burying it in an organic substrate. This is an anaerobic sulfate-reducing bacteria bioreactor. How effective can a sulfate-reducing bioreactor be? Can we call in Sulfur Man to take care of the problem? Let's see. Well, here is that Argo tunnel, a makeup of water that we saw before. And after being treated by the sulfate-reducing bioreactor, the pH is 6.6. Here are the stream standards. 0.5 milligrams per liter of iron, here's the stream standard. Manganese, we didn't do a very good job. Actually, manganese sulfide is not stable under anaerobic conditions, so we don't treat manganese very well. But we did a pretty good job on most of the metals in the treatment. Now, that's anaerobic treatment. There's also briefly aerobic treatment, where you have a series of cascading water over rocks, where you use oxygen to precipitate things like manganese that did not come out in the bioreactor, that will come out as a manganese oxide. And here are some of the so-called rock filters or aerobic cells. The truth of the matter is, it's no longer a one-step system. It's a multi-step system with aerobic cells and anaerobic cells. Okay, so what do we know about these passive systems? There's no cookbook yet for building them. You need to make calculations to decide how big these systems are. Each one is going to be different. They're now multi-step systems. Here's one that has an anoxic limestone drain, followed by aerobic cells, and it's an aerobic system, and then it feeds into an anaerobic system. So it's a multi-step system, and that is the talk for now, and I'd love to answer any questions you might have.
Okay, questions coming up. Remember to say your name. Is the mic on? Yeah, the green light is good.
Hello, my name is Emery, and just had a question. I didn't know if you ran across any, because I know we talked about, as far as solutions-wise, just as far as the streams continuing over time and things precipitating out, or with the different treatments. But have you ran across anything, or is there anything in the realm of like preventative? Like, I know it's not really probably your field, but as far as preventing the leakage in the first place, I don't know if you've like heard anything, or maybe it's just like not even existent. Just the questions.
You have a very good question there. It's very difficult to prevent the generation of acid mine drainage once you have all the mine workings in place. You have all these voids inside the mountain, and air is getting in there and water's getting in there. And if there's pyritic material, you're going to get AMD produced. Now, what they do is, as a temporary measure, as a temporary expedient, is they put these bulkheads, these plugs into these mines. And that will back up the water in the mines. Now, the hope is that if the water doesn't back up too fast, too much, that eventually the reactions will consume the oxygen that's in the water and will slow down and it won't be as bad. People have actually injected foam trying to cover the surfaces of the rock to keep the oxygen from contacting the pyrite. That hasn't been very effective. We actually injected composted livestock manure inside these mines behind one of these plugs or bulkheads, hoping to consume the oxygen as the organic matter decayed. But as soon as it decayed, the reaction started again and we got acid mine drainage. It's very difficult to prevent. Basically what they do is put in a plug, put pipes in the plug, and put a treatment plant outside, and then they can meter the water out from that bulkhead into the treatment plant to treat the water in perpetuity before it gets into the stream.
Hello, my name is Jesse. I had a question. In Jamaica, in the island of Jamaica, there's a lot of bauxite mining, and because of this, they call, well, at least my mom tells me, they call them acid lakes.
Yes.
And they just form because of all the waste, and there's stories about people just driving over a cliff into an acid lake and then they disappear. Is it possible that acid lake could dissolve a car or even a human body?
You know what? These bauxite mines and the aluminum processing produces a waste called red mud. And they may call them acid lakes. In reality, they're exceedingly alkaline with pHs up around 12, which can be just as corrosive in that direction as acid is in the other direction. And I can see the metal in a car gradually dissolving with time in such a pH of 11.5 or 12. And that red mud is nasty stuff. And it's just going to sit there. There's nothing you can do with it. So it's my brother lives in St. Croix in the Virgin Islands, and they had an aluminum processing plant there with the same red mud problem that you're talking about in Jamaica.
Yes, I was listening to, I'm sorry, I'm Dana. And you said that the problem with the concentration sort of washes itself out in a 2-day period and things are back to pretty close to normal. But my guess is that anything living is dead. So how long does it take for the living things to come back? And then the second question is, the people who open up the mine and expose the pyrite are doing that because it makes money for them. But who comes back years later and makes these plugs and continually puts manure in there and tries different kinds of things to fix it? Who's paying for that?
You are. We are. Okay, this is a very astute question, really. The fact is that well, the first thing, to my surprise, when they did the testing down around Durango, Colorado, where the plume went by, and people were yelling and screaming, "It's going to kill all the fish." It did not kill the fish in Cement Creek because all the fish are dead in Cement Creek. Cement Creek's been receiving that water for about 100 years, and there are no insects, there are no fish in Cement Creek. But in the Animas River, there are, and it's stocked. And they went in and they took fingerling trout, which are very sensitive to pollution, in these cages, and they put 107 fingerling trout in cages into the plume of pollution. And one died immediately upon immersal, and not one other died over 6 days. And what they said was that there was no evidence that the plume was toxic enough to actually kill the fish in the Animas River. And that, frankly, surprised me. They have done further tests like that, and it's back to pre-spill levels, but the fish didn't die, and the trout that were in there didn't die. They've taken samples of fish and fish tissue to see if metals have picked up in the fish tissue, and they haven't. They're at below detection limits. So the effect on the fish out in the Animas River, even in the plume, was not very significant. But the question you have about who's responsible, do you know that this mine stopped operations in 1923? And so when EPA or Superfund tries to go after the liable or responsible party, who do you go after? And the answer is that's why you have Superfund. It's a pool of funds, so EPA can get in there and temporarily stop the leaking with one of these bulkheads while they litigate trying to find out who the responsible or liable party is. And it is a major, major problem. Somebody said to me, I had an email that said I was a mouthpiece and puppet of the mining industry, and I was defending them when I said that I didn't see any long-term effects. And I said, well, who am I working for? The company that worked here stopped in 1923. The big problem is there are anywhere from 48,000 to maybe 161,000 abandoned inactive mines in the United States. And until they dig up the funds to make a concerted effort to mitigate these areas, to put the treatment systems in, to reclaim the areas around them, this is going to be an ongoing problem.
Hi, I'm Allie. I was just wondering, so we see this yellow color here, and we see it red in other places. Is there any specific chemical difference that the oxidizing iron is different colors?
Yes, it's really the amount of iron that's present. I had another slide where the water is red-orange, and I mean it's almost beautiful. What a color! But it's almost red, and it was from an iron mine up in Canada, and it was the sheer amount of iron that was present that gave it such a dark cast.
My name is Emily. All these pictures, the water's so colored. How long after a major spill will it take for the water to return to like its more normal color?
It depends on what the flow is and how big the spill was, and over what period of time the spill took place. If you have an instantaneous spill with a big peak, like I showed in that slide, it may go by really fast in hours. If you have a spill that's continuous all day, it may take days and days for it to go by. If the if the flow of the stream or river is high, it'll blast on through pretty quickly. If the flow is low, it'll hang around for a long time.
Hi, my name is Gabriel. I lived in Colorado for quite a while, so I was able to see how many thousands of mines were there. And I was wondering, at what point are you able to determine whether or not building facilities to mitigate the drainage from these mines is more environmentally detrimental than the systems themselves are able to fix?
I think it comes down to the fact that there's going to be disturbance at the mine if you're going to build a treatment facility. Now, not every mine is spilling acid mine drainage. And in fact, the Gold King mine was a pretty dry mine in terms it wasn't spilling very much water until they put the plug in the Sunnyside mine, which is connected to the Gold King mine. And water has a nasty habit of finding the path of least resistance, which was building up behind that plug and coming out the Gold King mine. Now, the point here is that there are maybe 230 mines that are continuously inputting acid mine drainage into streams in Colorado that we know that if you get up there and put in a treatment facility, that you can improve things. These areas generally are so utterly disturbed by the tailings, and some of these tailing storage facilities cover hundreds, if not thousands of acres that you're really not disturbing very much. A big problem comes in when, if you're at 12,000 feet, how in the world are you going to build a $5 to $20 million commercial treatment facility at 12,000 feet? You're going to have to build roads, get equipment up there, have access for people 24 hours a day, 7 days a week, all year round, and it becomes very problematic. So generally speaking, your construction of mitigation factors are like a treatment facility or a reclamation of the area is not going to make the problem worse. Generally, the problem will be improved. The biggest issue is money. The Government Accounting Office estimates it would cost $24 to $54 billion to clean up these abandoned inactive mine sites, and I think that's a low estimate.
Hello, my name is Kadra,
Hi.
and I was hi. You mentioned that you took 4 years to test the plants and the tissue and to see how much they were taking in. But my question was, what happened to the people in that area? What did you, was there any type of supplemental help given to them because they're without water? You know, they need that to survive.
That water. Now, are you speaking of the Big Five tunnel where we're doing the experiments? Okay. Right. Okay. Now, that water has never been used by the people there. What was happening is that nasty water was going continuously into Clear Creek. And Clear Creek, very little could grow. They'd have to stock the fish, and the fish would die. But nobody was using that water. That tunnel was built underneath most of the mine workings over a 120-year period. And it was built to drain the water from those tunnels so they could work dry. And so it drained all these tunnels with all that pyrite, with the acid mine drainage that went right out to Clear Creek, but nobody used that particular water. The water was taken in other locations, treated, and then that was for the water supply for the people in Idaho Springs. The water was eventually treated by a conventional treatment facility, so it wouldn't exceed standards going into Clear Creek, and Clear Creek has since cleaned up very considerably.
Hi, my name's Ryan, standing in the back here.
Yes,
Great
sir.
talk. Question about maybe to help neutralize the water. Has anybody studied what's this extra stuff we have in the atmosphere? Oh, carbon dioxide.
Okay.
I wonder, is there a way to, has anybody looked at carbon dioxide as a treatment to help neutralize?
We actually use carbon dioxide to Oh, okay. We've actually used carbon dioxide to acidify water. Carbon dioxide, the higher the level. No, it doesn't. Carbonates do, but carbon dioxide, if you add carbon dioxide to water, it forms carbonic acid. And if carbonic acid wants to identify itself as a self-respecting acid, what does a self-respecting acid do? It dissociates. It gives you hydrogen ions. So when you take water at 25 degrees C, pure water, in equilibrium with atmospheric CO2, the pH you get is 5.6 to 5.7. It's acidic. So CO2 actually will make your water more acidic.
But if you're dealing with water that's at 2,
Yeah.
you know, if you're dealing with acid drainage water that's at a pH of 2, you could then help bring it back up to at least 5, and then you could use lime to bring it back up to 6. I just wondered if there was something like that just to help. We could use that's definitely more, that's less acidic than acid water.
You know, the CO2 by itself wouldn't do what you want it to do into the reactions. At that point, it would just Yeah, go ahead.
The bicarbonate you could put into play.
Bicarbonate you can. Absolutely. You can put in bicarbonate, you can put in let's see, you can put in carbonate, you can put in bicarbonate. The carbonate is CO3 2-, and that would pick up 2 hydrogen ions and reduce acidity. A bicarbonate would pick up 1 hydrogen ion and reduce acidity. Carbon dioxide would dissolve, and only to a level of saturation, and nothing really would happen under those conditions.
But using equilibrium, if you could drive it into the carbonate, then as the hydrogen carbonate ion would react. I just wondered if anyone had looked at using some kind of a buffering system triggered by carbon dioxide.
No, I don't think anybody has looked at using CO2.
That might be all of our questions for today. I'll turn it back over to Dr. Murray. Oh, no.
All right. If there are no more questions.
Wonderful questions, by the
I
way.
want to thank you very much again. I think this was a really great lecture to start off our series. AU for gold, you live in golden. It's all golden all the way around.
And anybody there who has other questions, if they want to contact me, feel free to do so.
I could send that email out to the students and others so they could get in touch with you. Are you teaching this semester?
No, I'm not. I'm in my transitional retirement, where I work full-time in the spring and not at all in the fall.
Okay. All right. Thanks again.
My pleasure. Thank you.